Welcome to video 2 of this series of videos on the fluids and electrolytes lesson. In this video, we're going to talk about how you can estimate a fluid's osmolarity clinically, and then, so this is again fairly clinically relevant. And then we'll talk about some examples of how water can move in the body. All body fluids have the same osmolarity. So if that didn't come across in the last video, I'm telling you now, if you take the plasma osmolarity, that's the osmolarity everywhere else, okay? It's going to be the total body osmolarity is equal to the plasma osmolarity is equal to the intracellular osmolarity is equal to the osmolarity pretty much everywhere else in the body, all right? All right. The reason is because you can't maintain great water gradients across membranes. The membranes are water permeable, and water is going to move until the osmolarity is the same. Plasma osmolarity is determined by sodium and whatever anion is associated with it, and that's because sodium is the largest component of the plasma solute. Okay, so if you know the plasma sodium, you can make a pretty good estimate of what the plasma osmolarity is, because sodium makes up most of that. So sodium is fairly easy to measure in plasma clinically. So that it accounts for, it along with its anions, associated anions, account for about 90% of all the solutes. So 2 times the sodium concentration in your clin path values gives you 90% of the plasma osmolar concentration. The other cations and their anions account for about 10 milliosmoles per liter. Okay. And so roughly, the plasma osmolar concentration is 2 times the sodium, which accounts for 90% of it, plus 10 milliosmoles per liter, and that'll give you, this is in millimolar or milliequivalents per liter, and that will give you the total milliosmoles per liter. Now that works in a normal person because all the other stuff's not really that high. But you should notice that occasionally you'll come across a situation where the osmolarity is high because some solute that's ordinarily pretty low gets really high. And the classic example of this is glucose and diabetes mellitus. So as you guys know, diabetes, the signs of diabetes, you've got high plasma glucose, it gets really high. So you can correct for that because you know what normal is, and so this is normal, and so this is accounted for by the previous calculation I just showed you, 2 times sodium concentration plus 10. So what you really need to do is add on the number of milliosmoles per liter that are accounted for by the extra glucose. That's the glucose, the concentration of glucose that you see in your evaluation minus normal. And normal is about 100. So if you divide by the molecular weight, 180 grams per mole, or in this case milligrams per millimole, that gives you milliosmoles per deciliter. Okay, and so basically 1 millimolar glucose is equal to 1 milliosmole. So if you know what this is, then basically you have the osmolarity. The actual formula in this case, completed out, and if you have a person with diabetes, the extra glucose will be calculated as the glucose that you measure minus the normal divided by this 180, but notice that this is milliosmoles per deciliter, so in order to make it milliosmoles per liter, you multiply by 10. And that gives you milliosmoles per liter, okay? So the full equation is 2 times the sodium plus 10 plus 10 times the glucose you see minus the normal glucose divided by 180, and again, that's relevant when you have a patient with diabetes, for instance. So some examples of water movement, okay? Let's talk about examples of fluid gain here. You can give a variety of different solutions, and you guys will find that to be the case. D5W is one of them. It's 5% dextrose, which is basically, as I said, glucose. Isoosmotic glucose, so it has the same osmolarity as the plasma, only it's all glucose, okay? As you'll see in a moment, you give this with some caution. Isoosmotic fluids, a good example of this, the one you'll probably use the vast majority of the time, isoosmotic sodium chloride, or normal saline, which is 0.9% sodium chloride. And you can't have there is such a thing as hyperosmotic saline, which is sodium chloride, but it's not isoosmotic to the plasma. It's got so much sodium chloride in it that it's hyperosmotic, okay? So let's talk a little bit about what happens. Let's say you give some D5W. Well, as I said, it's dextrose, but really what we're talking about is just isoosmotic glucose. So you give the glucose, and this will trigger an endocrine response to accelerate glucose uptake and storage. And don't worry about the mechanism here. The GI, the food to fuel block is on its way, and that's trouble enough for another day. But take my word for it, this is what happens. And the glucose is actually used by cells, and that is probably the vast majority of the time, that's what you're going to be accomplishing here. Once it enters the cell, it exerts no net osmotic effect. In other words, it's effectively cell permeant because it's going into the cells and it's being used by the cells, okay? So what you did was you gave a bunch of glucose. It's being utilized by the cells, okay? And so it really, once it enters the cell, there's no effect on the osmolarity at all. And what you're left with on the outside of the cell is the water that you gave, okay? The dextrose is basically gone. And what you've effectively done is you've given 1 liter of water, okay? Have you ever heard of a physician giving anyone 1 liter of water? I hope not. Not IV, because that would be very bad, okay? The reason why you don't do that is because that water dilutes pretty much everything in the extracellular fluid, okay? And specifically, it dilutes all the impermeable solutes, which means you're creating an osmotic gradient, where the osmolarity is low on the outside of the cells, the extracellular fluid, high, relatively high on the inside of the cells because it didn't change. What that means is that water will flow from high concentration to low concentration, from low osmolarity to high osmolarity, and it's going to continue to flow until that osmotic gradient is gone. And so water enters the dilutes the fluid in all the compartments, okay, not just the plasma, everywhere, because water is moving into the cell. Well, if water is moving into the cells, that means your cells are swelling. That's probably not something that you want to do a lot of, which is why you usually don't give IV water, okay? If you do give D5W, you're usually pretty careful with it. And their physicians, well, the physicians, I'll leave it to them to tell you what the appropriate conditions are to give that. But this is why you don't want to, just give a whole lot of it really rapidly. If you give it really rapidly, you're going to cause the cells to swell, and it's going to be a really bad thing. More likely, you'll give it quite slowly, and often, I'm told, you'll cut it with an isoosmotic solution. All right. But we'll leave that to them. Just know that when you're giving it, you're effectively giving water. All right? What about isoosmotic sodium chloride? Well, the cells are functionally impermeable to sodium. So the sodium remains in the extracellular fluid along with the chloride, is associated anion, because you have to maintain electron neutrality. The fluid is isoosmotic, okay? So what that means is that if you give somebody sodium chloride and it's isoosmotic, it's the same osmolarity as the plasma, and that's the same osmolarity as the inside of the cell. so no water will move as a result of that, okay? The sodium chloride and the water that went in with the sodium chloride just redistributes within the extracellular space. And so the net outcome is to increase the plasma volume and increase the extracellular volume without changing the intracellular volume at all. In other words, your cells don't swell and they don't shrink, which is often something that you're going to want, okay? And for hyperosmotic saline, the sodium chloride's higher than the normal plasma osmolarity. So again, your sodium is cell impermeant. So an osmotic gradient is produced when you give this to a patient. And this raises the tonicity, the osmolarity, of the extracellular fluid. So we say the extracellular fluid is hypertonic. Okay, and as you know, that means that it causes cells to shrink, and sure enough, water will move from low osmolarity in the cells to high osmolarity outside the cells, and the extracellular fluid will go down, and your cells will shrink up. Okay, and again, that will happen until the osmotic difference is gone. So in the end, the osmolarity is somewhere between the original osmolarity that you started with in the plasma and the concentration of the saline that you gave, which means it's going to have a higher osmolarity, and the cell volume will shrink. The extracellular, well, both compartments will shrink. Okay, the extracellular compartment is increased because you infused a bunch of fluid. But it's increased even more because you've moved fluid out of the intracellular compartment. So the cells have shrunk. So you added a bunch of water with your hypertonic saline, and then because it was hypertonic, the fluid moved from the inside cells to outside the cells, and your plasma volume went up even more. Okay, so you really expanded plasma volume in this case. All right. That's all I've got for this video. We'll wrap this up with a video on the consequences of the osmotic changes and then of changes in fluid balance. And that'll be it. Thank you.